This is an overview of College Trigonometry version 3 by Stitz and Ziegler. 10.3, second video, 6 circular functions and fundamental identities. In this video we'll be covering the fundamental identities. The Pythagorean identities. We start out with cosine squared plus sine squared equals 1. This is the one to memorize. You don't actually need to know the rest of these because you can work them out from this cosine squared plus sine squared equals 1 very simply. For example, to get this common alternative form, solve for cosine squared. To solve for cosine squared, you subtract the sine squared and you get 1 minus sine squared equals cosine squared. Or if you solve for sine squared and subtract the cosine squared, you get this identity, sine squared equals 1 minus cosine squared. Now for the tangent identity and the secant, what we will do, I'm trying to erase that, there we go. We will take cosine squared theta plus sine squared theta equals 1, and we will divide by, to get a tangent, we would divide by cosine squared on this one. You have to do that on all of them. And what you get is 1, let's see, where is it? There it goes, 1 plus tangent squared equals, and this is reciprocal identity, secant squared. So you can just have this one memorized, divide by cosine squared, and you will get number 2. If instead, trying to erase, it doesn't look like it's going to work. Instead, if you were to divide by sine squared, you would get the third identity, number 3. This would be 1. There's your 1. This is cotangent squared, and this one is 1 over sine squared cosecant squared. So depending on if you divide by sine squared or cosine squared on your original number 1, you can get the second and the third one. And then the common alternate forms, take this one and solve for 1. Subtract the tangent squared, you got that one. Or solve for tangent squared and subtract the 1 and you have this one, etc. The common alternate forms are just moving terms around. So there's really only one to memorize in this section. I highly recommend you memorize that one and learn how to get the other ones very quickly so you don't have to over-memorize. Pythagorean conjugates. If you have a 1 minus cosine theta and you can multiply by a 1 plus cosine theta, magic happens in the form of you get a fundamental Pythagorean identity. In this case, conjugates multiply together. You will FOIL these. First is 1, outer and inner products cancel, and then you get minus cosine squared, and this equals sine squared. So if you have a 1 minus sign or a 1 plus sign, and then you can multiply by the other conjugate, then again this Pythagoras fundamental Pythagorean identity magic happens. So you can get used to the seeing when you have, there's no squares in any of this stuff on the left, no squares. But you multiply by the conjugate. They're all binomials, 2 terms, 2 terms, 2 terms. You multiply by the conjugate, and then you get the square stuff that the fundamental Pythagorean identities can then reduce in one way or the other. This is a great tool for the identities that are coming up in this section. When it comes to verifying identities, you'll try working on the more complicated side of the identity, usually. Sometimes people choose the easier one, but it's harder to complicate something than it is to simplify something. Use the basic reciprocal and quotient identities to rewrite functions on one side of the identity to look like the ones on the other side of the identity. Simplify anything that might happen. Add rational expressions, so add fractions with unlike denominators by obtaining common denominators. So you'll be adding fractions with identities, but you will look at the other side of the identity, and if the other side only has 1 term and the side you're working on has 2, then you know to add fractions. The Pythagorean identities, to exchange sines and cosines, etc. Multiply in the numerator and denominator by conjugates so that you can then use the Pythagorean identities. And you will always be working on one side at a time. So you work on one side and you get stuck, then go to the other side and work only on the other side for a while, and eventually you will find a spot where both left and the right sides match up. That is called verifying an identity. A lot of times people will choose to rewrite everything in terms of sine and cosine. It isn't always the best way, but sometimes it is, and it allows you to get to the formulas that you're more likely to have memorized on quick reference. Now we take a look at beyond the unit circle. So we discussed that cosine, and this is in the past section, cosine theta was x on the unit circle. But then when we were off the unit circle, then it was r cosine theta equals x. And on the unit circle, r would be 1, and so these are actually the same formula. This is a more general form. The beginning of this section, we went over, for example, that secant was 1 over x. It's actually r over x if you're not on the unit circle. And you could solve for r on the equation of a unit circle and rewrite it in this form if you choose. And cosecant and tangent and cotangent. So if you're not on the unit circle, tangent and cotangent don't change, but secant and cosecant do because they have an r involved. If you're working with a triangular notation rather than a unit circle notation, I've already discussed in a past section, so toa. Now we can take a look at the tangent. Tangent is opposite over adjacent. So opposite, if from theta's perspective, the opposite is b, and the adjacent is a. So tangent would be b over a, and that's all that's going on in this identity. The reciprocal cotangent, therefore, would be a over b. Cosine is adjacent over hypotenuse, that would be a over c, so its reciprocal secant would be hypotenuse over adjacent, c over a. And cosecant. Cosecant is the reciprocal of sine, opposite over hypotenuse, so cosecant will be hypotenuse over opposite. Hypotenuse over opposite. So these follow directly or indirectly from SOHCAHTOA. It's a nice way to remember this. When dealing with domain issues of periodic functions, we often have an infinite number of divide by zeros. So we might find that t cannot equal pi halves or negative pi halves, 3 pi halves or negative 3 pi halves, etc. All the odd pi halves. So on the number line, we have all these holes in the domain. I really like this notation. I think it's clear. The dot 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 suggests that you're not writing everything down, but that hopefully the pattern is clear. You can go to interval notation. Again, all the odd pi halves are where the domain stops and starts. So we have the union. There's an infinite number of separate intervals here. For example, the minus pi halves of pi halves is right here. Because of the hollow dots, there are soft brackets. But then right on the other side of pi halves, it starts back up again. So we continue to stop and start at all these values. This book goes over an infinite union notation. So the extended interval notation, union, that's what the infinite unions are. From negative infinity, dot, dot, dot to the left, to positive infinity, dot, dot, dot to the right. 2k plus 1 is an odd number. Pick any k you want, plug it into 2k plus 1, and you'll get an odd number. So this is an odd pi halves to the next odd pi halves. That notation is a very condensed notation of this concept. And you will see this, and I wanted to just do an overview for you. The summary of the domains and the ranges of the circular functions. We've already discussed cosine has an infinite domain, and it goes between -1 and +1, as does sine. Secant, because it's divided by cosine, and tangent, because it's divided by cosine, will have the same domain. Notice the domains are the same, because they're both because of divide by cosine. And cosecant and cotangent will have the same domain as well because they're both divided by sines. So you don't have to memorize all of this. If you choose to memorize some of this, you can use these patterns to help you to realize there's only two distinct issues here. Odd pi halves, and these would be full pi halves like pi, 2 pi, 3 pi, 4 pi, etc. The ranges. For secant, it's reciprocal of cosine. It basically stays outside of this range. So it's everything outside of. However, at -1 and +1, it does have dots, -1 and +1. And cosecant is the reciprocal of sine, the range from -1 to +1. Cosecant is outside of that range. Tangent has infinite range, so does cotangent. Alright, that completes this overview video.